Hey there, guys. So today is Monday, April 19th. We're still working on Chapter 7. We're trying to finish this one up today. I wanted to go ahead and do a video so that I can make sure that I cover everything. Make sure you guys are looking at the NIMSY notes. I was going to try to cover most of the stuff that's in the NIMSY notes with you guys, but it's not really going to be enough time. So we're trying to, go ahead and move on to the next chapter. We've already spent almost 2 weeks on this chapter, and I realize there's some stuff that we're seeing that's new that you guys haven't done. So make sure you guys are doing the NIMSY notes on Chapter 7. So our assignments for today is going to be the warm-up. This is due during class. I put 4 or 5 easy ones in there, and then I put one kind of harder free response question. So we'll do those. I'm going to share with you guys the Chapter 7 free response packet that's got a ton of free response questions on Chapter 7. And then I'm going to give you guys the answer key. And that'll really help you guys study for this chapter. And make sure you guys see some advanced problems. Because this chapter is really tough on the AP test. Let's see. Chapter 7 NIMSY notes are going to be due Wednesday. Wednesday's a half day, if you guys remember. So we won't be able to do a whole lot Wednesday. We're going to start Chapter 8 on Wednesday, I believe. Or maybe continue Chapter 7. We'll see. Chapter 7 quiz that I've been talking about for the 2 days now. This one's going to be due Friday. So we're going to go over the stuff in this video to help you guys get started on that quiz. I'll do an example. We'll talk about the trends. Everything you guys need to know about electron structure on that quiz is going to be in the warm-up that we did today. And it's also, I'm going to do an example of the Chapter 7 quiz. I'll do an example with carbon. Okay. Awesome. So here's what we want to cover today. I want to focus on periodic trends for a while. I want to hit the electromagnetic spectrum and wave equation, make sure you guys understand that kind of stuff. And then I'll show you guys a video on PES diagrams. I'm not going to cover PES diagrams because I actually found a video where a lady covers it beautifully. So I'm going to let you guys watch that video to see how to do PES diagrams. One second. There we go. Alright, so principal energy level. Real basic. We've been talking about this a lot, but now I want to relate what we've been talking about with the periodic table. So we've got our periodic table here. Isn't that nice? There we go. There are 7 energy levels on the periodic table. Okay. As we said before, this is the N. For principal energy level, it's the first quantum number. Principal energy level on the periodic table is the row it is in or the period that it's in. Alright, these rows are called periods. They go from left to right. As you move down the periodic table from the first energy level of hydrogen down to lithium, down to what's next, sodium, as you move down the periodic table, you're going to increase the number of shells. Okay, as you increase the number of shells, the energy of those shells actually increases, but the energy required to remove an electron from that atom actually decreases the farther you get from the nucleus, which would be at the center of that atom, that dot that I just put. So there's 7 energy levels, and you have electrons in each of them, 2 in the first one, 8 in the second one, and then pretty much 18 after that. And we know that it's not just S shells. We know that the first shell, we have the S. The second shell, we have the S and the P. So we just know that these shells get more complicated shapes. And then third, we get a D. And then fourth, we have S, P, D, and F. And so we can hold an increasing number of electrons in increasing energy levels. So I wanted to show you guys how the energy levels show up on the periodic table, and we'll relate that to some of our trends in a little bit. And we want to be able to use these trends to try to explain a lot of the things that we're seeing. So we want to be able to explain the trends and explain some weird exceptions and some weird things that'll happen. Alright, valence electrons. You guys know this. If you could look at the periodic table here, I guess I could have put a periodic table on these slides instead of having to draw one. If you look at the group 1 here, you've got hydrogen. Every element in group 1 has 1 valence electron. So that means that on the outermost shell of the electron, there's the nucleus in the middle, here's the outermost shell, for example, it's got 1 electron hanging out there. All right. If you go to the next column, these columns are called families or groups or columns. The second one is going to have 2 valence electrons. Group 3 is over here by boron. It's going to have 3. Carbon family is going to have 4. Nitrogen is going to have 5. Oxygen, oops, that's a 6 there. Oxygen is going to have 6 valence electrons. Fluorine, the halogens are going to have 7 valence electrons. And then helium and the noble gases will have 8 valence electrons. There we go. So helium, neon, krypton, all of them. So as you move this way across the periodic table, you are increasing the number of valence electrons, which means that you are filling that outer shell. So if you look at hydrogen, it's got 1 electron in that outermost shell, and that 1s. If you look at helium, you look at the 1s, it's going to have 2 electrons. So it's going to be 1s2, 1s1 for hydrogen, right? So we're going to have 2 electrons in that helium atom. If you look at lithium, lithium will have 1 valence electron in the 2s. So it'll be 2s1. It'll be hanging out there. If you go to boron, boron will have actually 2 electrons in that 1s. Well, what's the next one? What's this element right here? I'm drawing a blank. Lithium, beryllium. So beryllium will have 2s2. So this is going to be beryllium. This is lithium here. The next element, so that's beryllium there. And group 2, it'll have 2 valence electrons. The next one is boron. So if you look at boron, it'll have the same 2s, but also kind of contained within that energy level, it'll also have 1 electron in that 2p. And so in total, the total number of electrons in the outermost shell here, which is technically the second principal energy level, it will have 3 valence electrons. And it's in group 3, so that makes sense, right? But 2 of those electrons are going to be in the 2s, 1 is in the p. Regardless of whether it's in the s or the p, either way, they're both level 2. And so total of 3 electrons in that level. And as you go from boron to carbon to nitrogen to oxygen to fluorine to neon, as you move that way on the periodic table, you are simply filling that outer shell. You have 2p1 for boron. This will be 2p2, 2p3, 2p4, all the way to 2p6. So you're filling that outer shell. Okay, now there is something else that's happening as you move across the periodic table. As you go from, let me change colors for this. As you go from carbon, who has 6 protons, to nitrogen that has 7 protons, to oxygen that has 8, to fluorine that has 9, to neon that has 10. As you go from left to right on the periodic table, you're filling that outer shell of electrons like we just discussed, but you're also adding more and more protons to these atoms, and so the nucleus in the middle is going to actually pull on those electrons more tightly. So there's going to be more attraction to those electrons because there's more charge in the nucleus. So if you have a +6 atom pulling on those electrons that are a certain distance away, if you have the identical atom essentially, and you have 7, a +7 charge, well, it's going to pull on those electrons a little bit more so. Okay, the attraction between 2 particles is equivalent or proportional to the distance between them and the charge. How much charge are they? And that's in terms of Coulomb. So this is called Coulomb's law. So it's charge divided by distance between them squared. And we'll hit that more when we talk about Coulomb's law in chapter 10 pretty soon. So after we cover bonding. But the attraction between 2 oppositely charged particles is going to be proportional to the charge. So the greater the charge, the more force of attraction or repulsion. And then the greater the distance between those particles, the smaller the force. Right, and that we usually call it Fc, the force of attraction between 2 particles. So the Coulombic force, Coulombic attraction, holding the electrons around the nucleus. So the greater the distance between these particles, the smaller the force of attraction. Yeah, as we move from left to right across the periodic table, we're going to be increasing the nuclear charge. Increasing nuclear. And I probably have a slide in here about this, and so I'll just skip that slide since we just covered it. So increasing nuclear charge as you go from left to right, as you go that way. Awesome. Shielding effect. Now this is kind of cool. And a lot of students have a hard time with this one, but it's real simple. If you look at the periodic table, let's look at hydrogen down to lithium, down to sodium. What's next? Potassium. As you move down the periodic table, there's an increase in shielding or effective nuclear charge. It's actually increase in shielding, so let's write that. Increase in shielding. And it's actually a decrease in effective nuclear charge. And I'm trying to remember what this is called. I think they call it EFF. So if you ever see that on the AP test, ZFF means effective nuclear charge. It is the attraction between the nucleus and these electrons that are out here zipping around. They're being held by opposite charges, right? The effective nuclear charge is how much of that charge is felt by the nucleus. Okay, and let me explain. So if we have hydrogen, hydrogen has one shell, 1s1, right? So it's only got one electron, and I'm not going to change colors, but there's one electron there. I can just put an E there. So one electron zipping around in that 1s orbital. If we look at lithium, lithium has two shells, and so there is a barrier between the nucleus and that outermost electron. And this barrier, this 1s, so this is the 1s here, and there's two electrons in there, and then there's 2s with 1 in there. So lithium's configuration is 1s2, 2s1. And so this 1s shell right here, let's actually change colors for it. I don't have my iPad, so just bear with me. So this shell is actually shielding this electron from talking with this nucleus. And so the charge felt between the nucleus and that electron actually goes down. The attractive force goes down because these electrons are in the way. And also this electron is further away. And so the force felt is going to be less. So it has less effective charge. And then if you go down to what's next? Sodium. This effect is even multiplied even more because now there's many different electrons between the nucleus right here and these electrons. Now there's two things, two shells. The 1s and the 2s are both in the way between the 3s and the nucleus. Right? There's a pull there, and so there's a shielding effect. So shielding increases as you go down. So as you go down the periodic table, shielding increases. And I usually use the word shielding for pre-AP or my regular students. And maybe we could call it effective nuclear charge. But effective nuclear charge, ZF, so the charge is usually symbolized by Z. The effective nuclear charge is actually going to go down. Alright, so as you go down, the shielding effect is increased, which means the nuclear charge is decreased. So nuclear charge decreases. Okay, the power of the nucleus to hold those outer shell electrons, it's less and less, and so it's actually easier for those electrons to leave. Okay, and this will explain a lot of our trends that we'll talk about. All right, so you got to understand as you move down a group or down a family on the periodic table, the shielding effect is increased, the nuclear charge is less, which means that there's less pull on those electrons. So it's not holding those electrons as tightly as it would otherwise. Also, as you move across the periodic table, remember that you're adding protons to that nucleus, and you're having more pull on those outer electrons. Okay, so let's erase here. So as we go down the periodic table, we have less pull, less nuclear charge, less pull on those electrons, meaning that the electrons are a little bit more free to leave or ionize. And as you go this way, from left to right, as you add protons, from carbon, which has 6, to nitrogen that has 7, to oxygen that has 8, and you keep moving this way, you're going to have more pull. Okay, and that's gonna cause all of these two trends here, shielding and nuclear pull, nuclear charge, are both going to determine all of our trends and explain all of our trends. Okay. Please stop me at any time if you guys have questions. Just let me know in the chat. Nuclear pull is what we've been talking about. As you move that way on the periodic table, as you add protons to that nucleus, you get more pull. And so if you're trying to explain something and you say, okay, I know as if I'm comparing carbon with 6 protons to fluorine that has 9 protons, I know that the nucleus of a fluorine atom is going to hold on to all of the electrons, whatever shell they're in, it's going to hold on to them more so than the carbon nucleus, because it's got more protons, it's got more charge, so we're going to have more pull. Okay. Okay, we talked about shielding. Oops, should be going forward. Atomic radius. Here's our first trend. If you look on the periodic table and think about these trends, let me just first tell you the trend. So the trend in atomic radius is that it increases down and it increases to the left. Okay, so increases down a group and it increases from left to, or from right to left. Okay, so if you look on the periodic table, the smallest atom is up here. The largest is down here. Francium. Francium right here, Fr, in group 1 is the largest atom. All right, the smallest atom up here is going to be helium. Okay, now I don't mean by mass, we're talking atomic radius. So think of a circle, and think of the nucleus as in the center of that circle. This is the outermost valence electron that essentially represents the end of the atom. Right beyond this is empty space. So this is the perimeter of that atom. The atomic radius is the distance between here and here, like a radius of a circle. Okay. Now let's think about why it increases down. So why does it increase down? So why down? Okay, well we said that as you move down a group, we have more shielding, less effective nuclear charge. Therefore, we have, so I can do the 3 dots like therefore we get less pull on the valence electrons. All right, so as you move down, you have more and more shells obstructing the nucleus and that outermost electrons. And I always like drawing this because it looks like a snowman, doesn't it? I always like drawing that. Give him a top hat and 2 eyeballs. There we go. So as you move down from the small shell to the large shell atoms, there's more distance between that, and they're shielded, which means that the pull of the nucleus is not as easily felt as it would otherwise be. These electrons in between them kind of interfere with that pull. All right, so as we go down, the atomic radius gets larger because the nucleus is pulling on the electrons less. That makes sense, right? All right, now why does it increase? Let's say why does it why does it decrease? I'm going to put it this way. Why does the atomic radius decrease to the right? Right, up here, let me change colors here. Up here, we said that it increases to the left, right? So why does it decrease to the right? It decreases to the right because as we move to the right, we have increasing number of protons, which increases charge. Which increases the pull. So let's think about that. It decreases to the right. So it gets smaller. So as you go from left to right and you go that way, you have more protons in the nucleus, more charge, more pull. Now here we just call it pure charge. This is not effective charge. This is just charge, because you're literally going from like carbon, which is 6 protons, to nitrogen, which has 7 protons. So you literally have more charge, more coulombs of charge. And so we're increasing that pull on those electrons. And so the atom gets smaller because there's more pull. More pull. That makes sense, right? As you have more pull on those electrons, it's going to hold them tighter. Right? It's gonna kind of watch after them like the nucleus is a mother and those electrons are babies. It's gonna hold on to those babies a little tighter as you have more protons. Okay, atomic radius, very cool. Ionization energy. Ionization energy is the energy required to remove an electron. So energy needed to remove an electron. So take a neutral atom and zap it and remove one of the electrons. The energy required to do that is called ionization energy, and it's usually kilojoules per mole. And you can actually have several ionization energies. You can have let's say you have a carbon atom. Carbon atom is going to have 1s2, 2s2, 2p4, right? And so the first ionization energy will be the energy required to pull that one off. And so it's going to be 1s2, 2s2, 2p3. Right? So this is going to be carbon neutral. This is going to be carbon with a +1 charge. Okay. Let's go ahead and take that and pull another electron off. 1s2, 2s2, 2p2. Well, now carbon's going to have a +2 because it has lost 2 electrons. And we continue. And actually, carbon likes to make a +4 charge, and you guys can see why right here, right? That 2p is completely gone, and it likes that. It likes to completely eliminate that 2p shell so that the only shell that remains is the 2s. And now the 2s, get this, now the 2s is a full outer shell, right? Remember how we're always saying atoms like to react and lose electrons or gain electrons so that they can have a full outer shell? Well, this is how it does it. It's going to lose that 2p. Now, carbon can just as easily gain electrons. So if we take a carbon atom, 1s2, 2s2, 2p4, it can just as easily gain one. So we can have a carbon -1 ion, 1s2, 2s2, 2p5, or it can actually gain 2, and it can have 2p6. And so carbon can actually become a negative charge as well. And so the ionization energy is the energy required to pull an electron off. The second ionization energy is the energy required to pull that second electron. Okay, if you look at the electronic structure here, you can tell which one's going to be the greatest energy. Okay, there's going to be a jump. So right here, we started with the 2p4, right? That's what carbon has, 1s2, 2s2, 2p4. We removed an electron, got 2p3. We removed an electron, we got 2p2. We removed an electron, we got 3p3. Now this next step, if we were to remove another electron, this would be, so this is the first, the second, the third, the fourth, and the fifth. No. Let me back that up. Where's my eraser? That's not right. This would be my first here. The first electron I removed, my second electron I removed, the third one I removed, and this would be the fourth. Now, let's say that we have this, 1s2, 2s2. We got a carbon with a +4. Let's remove another electron. Let's figure out what that fifth ionization energy would be. And we're going to compare the relative energy of that pull compared to these others. We're going to have 1s2, 2s1. Okay, now think about this. You got 2 electrons in that 2s. that 2s is closer to the nucleus of that atom than the 2p. You can think of the 2p as being a little bit further out. And so if you're going to pull those electrons from that 2s, you're going to have to pay for it, right? It's going to cost quite a bit. And so there's a cost to pull this 2s. If you want to remove that electron from the 2s, it's going to cost you. So there's going to be a jump in energy between these two. And that's because the first couple of times that you are pulling electrons, you're pulling from this outermost 2p, which is way out here. And so it's going to cost, and it's going to increase as you pull electrons, and it's going to have like a linear relationship between the cost. It's going to like double, right? Or whatever the change is, it's going to be a constant rate, kind of, okay? We can assume that. Now, once you get to this one, and you try to pull from this 2s, since it is much closer to the nucleus of that atom, it's going to be difficult to remove. And there's going to be a exponential change between these two. And so if you were to look at tables of ionization energy, you would see a big jump. Okay? And we got to be able to identify those jumps. Okay? When you've pulled, so once you finish pulling everything from the valence shell, okay, so it costs some energy to pull from the valence shell, and it's all right. And it's a you know, a decent amount of energy. But if you start trying to pull on those inner core electrons that are further in the atom, it's going to cost a lot more. All right, so we got to understand ionization energy. Ionization energy is, again, it's the energy required to remove an electron from an atom. Ionization energy is going to increase up and increase to the right with no exceptions. So this means that on the periodic table, the highest ionization energy is going to be helium. The lowest is going to be francium. Okay. Why does it increase going up? Well, we know that as we go down the periodic table, we have more shielding, which means less pull. So if those electrons are held less tightly from the nucleus, the energy required to remove them will decrease. So as you go down the periodic table, it's going to decrease. Right? That's why we say up here, that's why I drew this arrow, is increasing up. The way that I like to do this is I like to only write arrows for increase. So it will increase up and it'll increase to the right. And that way when we draw an arrow, it only means increase. So I'm going to try to stick with that, okay? So if it increases up because you have more pull, it's going to hold on to them more tightly. Also, as you go up, the atoms get smaller. Helium is a tiny atom. Helium has 2 protons in it, and it's got one shell there, the 1s, and it's got 2 electrons in there. It's a tiny little atom, and it's going to hold those electrons very tightly. Okay, why does ionization energy increase this way? It increases that way. Why is that? Well, as you go from one element to the next, you have more charge in that nucleus, right? More charge. Well, as you have more charge, that nucleus is going to pull those electrons in a little bit more so. So that means more pull. That means it's going to cost more energy to remove an electron. And so the ionization energy, the energy required to remove an electron, will cost more as you go from left to right. Okay? All right. That's a tough one. Electron affinity. This one has a very similar trend. Also notice that if you go back, notice that these two, ionization energy increases up and to the right. Most trends have this exact pattern. It increases up and to the right. Notice atomic radius. It increases down and to the left. Completely opposite. So atomic radius is the exact opposite trend as ionization energy. And they have no exceptions. Okay? So as you go up, they're going to increase, and as you go to the right, they're going to increase. Some of these other trends have exceptions, like electron affinity. Electron affinity has some exceptions. So electron affinity is the energy associated with an atom gaining an electron. So conceptually, it's kind of like the opposite of ionization energy. You take a neutral atom, and it's chilling, give it an extra electron. How much energy does it take to absorb that electron? That's electron affinity. It increases up, has the same trend as ionization energy. Okay. And actually, let me look this up because I want to make sure that I don't mess this up. It increases from left to right, pretty much for the same reason ionization energy increases up. Let's see. Maybe if I can look at an picture. Okay. I'm just gonna assume here, and I'm pretty sure I'm correct. So in general, it is going to increase up and to the right for the same reasons. As you go up the periodic table, you have less shielding, therefore more pull, and so the energy is going to be greater. And then the same thing to the right, you're going to have more electron affinity because you have more charge in the nucleus, so then it's going to cost more energy. The only difference between electron affinity and ionization energy in terms of the trend is the fact that the noble gases, group 8, do not have electron affinity. They are not going to take an electron, right? They are full, they have nowhere to put it, they're happy, and so they don't have electron affinity. Other than that, it increases up and to the right, and so you might expect the highest, the element that has the highest, you might expect fluorine to have the highest because it is the furthest up and to the right of the periodic table, right? If we look at our periodic table here, see, fluorine is the highest other than the noble gases, so we might expect fluorine, but actually chlorine has the highest. And there's an interesting thing about that. And let's look at that. I had it pulled up just a second ago. Where is it? Fluorine versus chlorine. Okay, let's look at this. This is interesting. And hopefully this doesn't get too beyond what we can understand. A fluorine atom has an electronic structure 1s2, 2s2, 2p5. It has 9 protons in the nucleus. The incoming electron enters the second level and is screened from the nucleus by the 1s2 electrons, or shielded. It's shielded from the electron. It therefore feels a net attraction from the nucleus of +7. 9 protons less than 2 screening electrons. Okay, I don't understand that part. In contrast, chlorine has the electronic structure of 1s2, 2s2, 2p6, 3s2, 3p2, 3p. So 3p, 1, 2, 3, 4, 5, with 17 protons in the nucleus. But again, the incoming electron feels a net attraction from the nucleus. There is also a small amount of screening or shielding by the 2s electrons. It will be approximately the same in both of these cases. It does not affect the argument in any way. The overriding factor is therefore the increased distance that the incoming electron finds itself from the nucleus as you go down the group. Yeah, so chlorine's larger. And so chlorine is actually going to have the largest electron affinity. If you look at this table, this graph here, chlorine actually has the most, and then fluorine is second. And it's because chlorine has a larger atom, and so there's more shielding. And so the energy is going to be lower. Okay, so again, electron affinity is the energy associated with absorbing an electron, and it increases up and to the right, but the noble gases essentially have 0 electron affinity. Okay, same exact trend as ionization energy, except the noble gases do not count. Okay, oops. Next one, now this is my favorite trend. This is going to be your favorite trend. This trend right here will explain almost everything in Chapter 8, electronegativity. Electronegativity is a tendency of an atom to pull electrons to itself. Okay, it's kind of like thinking, how much of a nonmetal is it? How much non-metallic behavior does an element have? Because that's what nonmetals do. They're going to pull electrons to themselves. So it's the non-metallic behavior. Nonmetals like to pull electrons to themselves in order to fill their outer shell. The more they're able to do this, the more electronegative they are. Okay, electronegativity is measured as a scale from 0 to 4. And you can look up that scale if you like. Fluorine actually has the highest, and then oxygen, and then nitrogen, and then chlorine. So that's the first four, and you need to know those. Very, 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 very important. First, most electronegative element is fluorine, and then oxygen, and then nitrogen, and then chlorine. So phone call is a good way to remember this. Or I just remember phone call. Those are the top four. And then it decreases down and decreases that way. So this is the least, and fluorine's the most. So again, francium is the least here. All right, it's got the same exact trend as ionization energy and electron affinity. It increases up, and it increases that way. But again, the noble gases don't count. They do not have electronegativity because they don't want to pull electrons to themselves. They're already full. So they're fine. They don't need electrons. Everybody else needs them, right? And they're trying to get those electrons to behave and be isoelectronic with the noble gases, right? They want to have the same electron configuration as the noble gases. And so they're going to react in order to do so. So electronegativity is the difference, is the tendency of an atom to pull electrons to itself or to behave like a nonmetal. That's the top four. It increases up and to the right. And we're going to be looking at electronegativity differences. So if you try to draw a compound like CH4 or CO2, we want to try to determine if these molecules are polar or nonpolar. And so we'll be looking at the difference between electronegativity between the carbon and the hydrogen atom here, or the difference between the carbon and oxygen atom there. And so we'll be looking at bonds, and we say, what's the difference in electronegativity? Is this a polar or nonpolar bond? And then once we know if it's a polar or nonpolar bond, we'll know what kind of forces are in the molecule. So we'll use this in our next chapter on, actually our next two chapters on bonding and on solutions and intermolecular forces. All right. Ionic radius. This one's cool. So we talked about atomic radius, and we said that the size of the atom actually increases down and to the left, right? And so we're saying that the largest atom is down here, francium, and the smallest is up here, helium, right? And so atomic radius has the same exact pattern. The difference is you've got to understand which atom is ionizing. So if you have a metal, let's think about metals. Metals like to lose electrons. And think about a picture of an atom. Think about an atom. Oh, you can't see that there, can you? So think about an atom here with a nucleus, and you've got these electrons hanging out in this. So let's say we're going to remove that electron, right? Metals like to lose electrons and to ionize. So let's go ahead and ionize this atom. There we go. What do you guys see? Did it get bigger or did it get smaller? Oops. It got smaller, didn't it? All right, and that's why. So you lose the outermost electrons, so the shell gets deleted, essentially. That's the way to think about it. And so they get smaller. So if you have a metal like sodium, the neutral atom of sodium is actually going to be larger than the sodium ion. And you guys can see that, right? Here's sodium atom. Right? And let's remove that and become an ion. You guys can see that it gets smaller. You lose that outer shell. So metals get smaller. All right, let's look at nonmetals. They will do the opposite. They're going to gain electrons. Okay? And so what you have in this case is here's our nucleus. Let's say here's our first shell, here's our second shell. Let's say we're going to take a fluorine atom and turn it into a fluorine ion. So it's going to be fluorine. It's going to have 1, 2, 3, 4, 5, 6, 7 dots. And then it's going to be fluorine with 8 dots and a -1 charge, right? So it's going to gain 1 electron. At first, we have 7 electrons in this outermost shell, right? Okay, let's pick up an electron from somewhere. All right, there's our electron coming in. Now we have 8 in here. Okay, so in terms of the shells, nothing changes, but now we have 8 electrons. All of these electrons are in the same shell, and so what are they going to do with each other? They're going to fight, right? They're going to repel each other, right? This guy is going to push away from this guy. This guy is going to push away from this guy. They're all going to repel, and that's going to blow this shell up. This shell is going to get a little bit bigger. And so as nonmetals gain electrons and become ions, they're going to become larger. So nonmetals get smaller. Metals get smaller. Nonmetals get larger. Okay. So if you're comparing ions that do the same thing, like if you're going to compare a sodium ion to a potassium ion, you're going to follow the trend on atomic radius. They're going to increase down and to the left. Okay, but what if you want to compare the ionic radius of a sodium versus a sulfur atom? Well, we know that this one's going to get smaller. This one's smaller than a sodium atom. Smaller. And then this one is going to be larger because it's gaining electrons. So we know that this one's going to be larger than this one. So we can compare different ions, whether they're metal or non-metal. So that's ionic radius. That's another tough one. Reactivity, okay. This one's real simple. Reactivity depends on what kind of element you are, okay. So let's look at the metals here. Metals reactivity actually increases down. Okay, a metal is able to react when it's able to lose that outermost electron. So think about a shell here. Right, we've got electrons hanging out here. If we can lose that metal, that's going to be reaction. So it's going to react when it loses that electron, because that's what metals do. They're going to lose that electron. The larger the atom is, the more shells it has. As you go down the periodic table, you're going to have more and more shells. And so the distance between the nucleus and that outer shell, it gets larger and larger. And so this little electron is so far away from its mother that the force holding it is just not as great, and so it's easier to react. So as you go down the periodic table, metals get more reactive. Now nonmetals, as you guys can guess, they will do the opposite. They are going to react increasing up. Okay, and let's make sure we understand this. As you go up the periodic table, you have less shielding. Which means more pull. So you have more pull in those electrons. Okay, so as you go up the periodic table, you have more pull in the electrons. Nonmetals want to gain electrons, and they have high electronegativities, right? Remember how I said electronegativity is kind of like non-metallic character. It's going to behave more like a nonmetal, so they're going to want to gain electrons. If this nucleus has more pull, then it is more easily able to pull electrons, which means it's going to be more reactive. So fluorine going to fluorine as an ion is going to be, so this is what fluorine will do when it reacts. It's going to have 8 electrons here. Of course, it's going to have 7 here. And so when it reacts, it's going to gain an electron, and it's more easily able to do that as you go up, and also this way. And then metals will increase in reactivity actually that way. So they're opposites, right? This one's pointing up. Nonmetals react as you go up to fluorine. Fluorine is the most reactive. Of course, this doesn't count the noble gases. They don't count. They're not going to react, right? For the most part. So fluorine will be the most reactive nonmetal. So as you go over this way to the periodic table and go up, it's going to get more reactive. Nonmetals. Now metals will increase down and this way. Okay, and you guys know that group 1 metals, the alkali metals, are the most reactive. You can actually put them in water and have them explode. All right, and I would recommend looking up that video. Look on YouTube and find a video of putting alkali metals in water. It's pretty cool. I'll share one with you guys. Okay, so that's metals reactivity and non-metal reactivity all in one. Metallic character increases as you go to the metals. So And I'll draw this one just for fun. So here's our periodic table. Metallic character will increase that way and increase down. As you get to this, it's going to be more metallic character, which means it's going to be more reactive. Okay. Non-metallic character will be the opposite. Non-metallic character is going to increase that way and increase that way, not counting our poor noble gases. They will not count because they're not going to react, right? All right, well, that's our trends. Awesome. There's my little man. Let's look at our NIMSY notes here, and let's cover some things. So electromagnetic radiation is a type of light. There's different types of wavelengths. It goes all the way from gamma rays, which have a wavelength of 10 to the minus 12, all the way to radio waves. So these are all types of light. The only kind that we can see that's visible is called visible light, and it goes from 4 times 10 to the minus 7 meters in wavelength to 7 times 10 to the negative 7 meters in wavelength. And it starts at purple and it goes through the colors of the rainbow. Okay. Here's the formula for velocity. The velocity of a wave of light is equal to the wavelength times the frequency. And actually, if you have light, it's going to be constant. Okay, so it's going to be 3 times 10 to the 8th meters per second. So that speed of light is constant. All of these waves move at the same speed. Well, if the speed is constant, velocity, if that's constant, then if this goes up, this goes down. So there's an inverse relationship between wavelength and frequency, and that's very important to understand. Okay, so wavelength is the distance between crest. We said the amplitude is the height of the wave. Frequency is how many waves per second, right? So you guys can see here. And I always like to ask my students this. This is always fun, especially my on-level chemistry. I ask them, look at these waves. Which one's the fastest? Which of those waves of light is moving the fastest? They always say this one. It looks like it's moving faster, right? And I was like, trick question. These are all waves of light, and they all move at the speed of light. No exception. So it doesn't matter. So there's just more waves per second, but it's still moving from left to right at the same speed. Okay. And the speed of light is fast, okay? How fast? It's hard to appreciate this, right? It's moving at 100, it's a little bit more than this, but it's about 180,000 miles per second. So think about something moving that fast. Think about a ball moving 180,000 miles in 1 second. That's fast, right? Okay, and we've got some examples here that you guys will see in the NIMSY notes. Energy is related to the, this is going to be the principal energy level times Planck's constant times velocity. All right, and so energy is proportional wavelength. It is proportional to frequency. So if you look up here, look at these. You guys may think that this one's faster, right? It may look faster, but remember they're all light, so they're going to be moving at the same speed. But this one actually does have more energy. This one has less energy. So the frequency is directly related with the energy, but it's inversely related with the wavelength. Okay. Let's see. Okay, so we learned that there's a minimum amount of energy that an atom can gain. It's either going to gain that amount of energy or it's not going to do it. And so energy is quantized, meaning that there's packets of energy. So an atom can gain a packet of energy or 2 packets of energy, but it's not going to gain like a packet and a half. So these packets are called quantums. And a quantum is equal to hv, where h is Planck's constant. This is just a constant value that you plug into equations to make the equation work, created by Max Planck. It's joules per second, and it's negative 10 to the negative 34. So atoms can only gain energy in packets of quantums. Okay, so only a certain amount of energy. Let's see. So Einstein called these particles photons. So these are massless particles of light called photons. The photoelectric effect is the observation that when light hits a surface of a metal, electrons are going to be ejected. So there's a relationship between light and metals and electrons, which is cool. Of course, there must be a minimum frequency minimum amount of energy for this photoelectric to occur. Once you meet the minimum energy, then you're going to see the photoelectric effect occur. Here's the energy of a photon of light, hc over lambda. So h is Planck's constant, c is the speed of light, and that's the wavelength. You guys know that E equals mc squared. Energy equals mass times the speed of light squared. That's Einstein's famous equation that proved that energy and mass are two sides of the same coin. If you rearrange this and solve for mass, we see that the mass of a light beam is equal to Planck's constant divided by the wavelength times c. So does a photon of light have mass? In this case, it does. So in summary, energy is quantized. It can only occur in discrete units called quanta, HV. That's Planck's constant times the frequency. Electromagnetic radiation or light exhibits wave properties and particle properties. So essentially, if you study light and look at it, it will look like a particle. If you study subatomic particles, it will look like a particle when you look at it. But then if you look away, it'll look like a wave. It'll behave like a wave. Okay, so this is the dual nature of matter and dual nature of light. All right, so since light was thought to be a wave, it now has certain characteristics of a particle. Then we look at de Broglie. So de Broglie substituted V for velocity and C for an object that is not traveling at the speed of light. He came up with the de Broglie equation. The wavelength of a photon of light is equal to the Planck's constant divided by mass times the frequency. Okay, so we've got some examples here. The more massive an object, the smaller its associated wavelength is, and vice versa. All right, so all matter exhibits both particle properties and wave properties. Okay, Niels Bohr studied the way that light interacts with atoms, and he realized that different atoms produce different light signatures. These are called absorption spectrums. This is a graph that shows how much energy is associated with a substance absorbing light. All right, and a line spectrum is a thin beam that is isolated thin beam by passing through a slit, then a prism or a diffraction grating, which sorts into discrete frequencies. So discrete frequencies are lines. And so if you study an element or an atom and you look at how it interacts with light, it produces a fingerprint. And you can study and identify different atoms based on their fingerprint by the amount of energy that they produce. And that energy that they produce, this is very important, the energy that they produce is going to reflect and be proportional to what we see in their electronic structure. Okay. Niels Bohr connected spectra and the quantum ideas of Einstein and Max Planck. The single electron of the hydrogen atom could occupy only certain energy states. So that's why we have energy shells, is because of this quantization of matter. Energy is only in packets. Only you can have electrons occur in the first shell or the second shell. There's nothing in between. There's empty space in between those two shells. Okay. Here's an example of a spectrograph. Kind of like, so think of this as hydrogen gas. I'm not sure what kind of spectrum this is, like what element this is, but this is an example. So you see different colors of light at different wavelengths. Our mother of all assumptions is that atoms are going to be in their lowest energy state unless they are disturbed. Okay, and so we know that they're going to occupy these different shells, and they're going to be in their lowest energy state. So we can write the ground state of electron configuration. You guys can look at this in the NIMSY notes. I'm going to skip some of this stuff here. I'm also going to skip some of this stuff on quantum mechanical model. So basically, Erwin Schrödinger studied waves and how they describe, kind of mathematically describe what we're seeing in the orbitals. And there's a solution to these equations called the wave function. And a wave function has a symbol here, which looks kind of cool. And it basically shows how, see this orange wave here? At at the principal energy levels, the wave function is actually going to almost nicely fit into that circle, right? So they're going to match. But then at fractions of it, it's not going to really line up that great. All right, and so this is again showing how energy is quantized. Those electrons are stuck in those shells. Okay, and we can study the wave function. This is a graph of it. So it's the probability of finding an electron, and it's measured based off the distance to the nucleus. So if we do this, we see a S sphere, and it's more dense in the center, so you're more likely to find an electron closer. And then as you go out, it kind of falls off. But there is an actual limit where this thing does, if you get beyond here, then you're in empty space. There's no electrons out there. So this is how we came across the orbitals. Okay, so this is what an orbital is. Let's see. So we talked about quantum numbers. I think we're pretty good there. We talked about the shapes of orbitals. Now here it is important to note that for the s orbital, you have the orbital wave, you have the orbital structure, and then you have nodes between them. And I talked about that before. So you have these gaps between them. Okay, and there's only one for each of them. When you have a p orbital, there's actually a plane between these two. So imagine taking a piece of paper and splitting these two in half. There's actually a plane right here where my mouse is that there's no electrons there, and so that's a node right there. And here there's a node so this one has a node in the z direction coming down. So imagine slicing it from the top down with a piece of paper. This one, it's going to sandwich in between there this way, horizontally, and then this one's going to be horizontally as well. And then there's 3 different nodes in the p orbitals. There's 5 nodes. Wait, is there 5? There's 4 nodes in the d, and there's even more in the f. There's 5 nodes. 1, 2, 3, 4, 5, 6, 7 nodes in the let's see. 8 sections, 8 nodes in the F. And so we can write electron configuration, talk about electron spin, magnetism. Oh, let's talk about magnetism. Diamagnetic means not magnetic. So magnetism dies. So if you remember, magnetism dies, diamagnetic, not magnetic. Okay? These are not magnetic because they have electrons that are paired up together, and so they're going to cancel each other out. So they're not going to be magnetic. Paramagnetic means that the atom is going to be attracted to a magnetic field. They're going to lose their magnetism when removed from the magnetic field. And this is because it has unpaired electrons. So it's going to be attracted to a magnet. Okay. We talked about how atoms have a plus up or plus minus spin. There's also ferromagnetic substances. Ferromagnetic substance will retain and remain magnetic upon introduction to and then removal from the magnetic field. So that means that they're going to be remain magnetic even after you apply it and remove it from the magnetic field. It will still remain retain that magnetism. And this is like a magnet, like iron, like a compass, right? Like a magnet. You put that magnet near a compass, and it's going to be attracted to it. Okay. Okay, that's about it. I just wanted to hit mainly the wave equation stuff. We'll talk about PES diagrams. We'll talk about penetration here. Yeah, and you guys will see this in the NIMSY notes. And I think that will be enough for us. But make sure you guys go through this. Here's the trends again, so if you want to go through this on the trends. Here's a nice chart showing the ionization energy. Notice that the noble gases have the highest for each of their periods, right? Because noble gases are full. They have full outer shells, and so it's going to be very hard to remove an electron from a noble gas. All right. There are some anomalies in here. There are some exceptions. So yeah, that's pretty much it, guys. Thank you. Y'all have a great one. Thank you guys for listening.